Moving on to what we call improper integrals. Okay, so let's go over some terminology. So remember, a definite integral is something from A to B, right? And this is adding up the areas of the rectangles from A to B, and this gives us a number, right? An indefinite integral is just integral from f of x, and that gives us just the antiderivative and plus c. Okay, so this is a number, this is an antiderivative. What is this? This is going to have something to do with infinity or negative infinity. So if I'm going to be taking the integral from a to infinity of a function, we have to rewrite it as a limit. We must rewrite it as a limit if I'm going towards negative infinity, because we do not treat infinity as a number. And they're called improper intervals, and we're going to be finding out if the limit exists. If the limit exists, then we say it converges, and if the limit doesn't exist, we say it diverges. So what I'm looking at, so let's just get an idea here with this function, f of x equal 1 over x cubed. So you know that looks like this, right? So what I'm talking about, if I'm taking the integral from 1 to infinity, is I'm trying to see if this area, right, starting at 1 and going out to infinity, if that infinite area adds up. Because the questions will always be converge or diverge. If convergent, evaluate or find out what it converges to. So it is necessary. So I'm going to be taking points off if you do not rewrite it as a limit. So the first step, you notice the infinity, and I have a horizontal asymptote, right? That's what we're looking at, is a horizontal asymptote at y equals 0. So that's how I've got the infinite area. So I start by taking away the infinity, and I put t up here where the infinity was, and I say take the limit as t goes to infinity. And then I take the antiderivative, right? This is x to the negative 3. So I took the antiderivative x to the negative 2 over negative 2 and then rewrote it, right? X to the negative 2, whoops, x here. I'm trying to write x to the negative 2 over negative 2. I put the negative exponent in the denominator, right? It's so useful to see what the fraction is. So I'm going to encourage you to do this. Now, plug in the top limit, put the t in, there it is here, subtract off, plugging in the 1, so here's the negative and then the subtraction, there's the subtract off, and then I kept the negative down here. Now I'm going to do what I know about limits, let t go to infinity. As t goes to infinity in this denominator, 1 over infinity goes to 0, so I'm left with this term, which gives me a positive 1/2. Since I get a number from the limit, I say this integral converges. Okay, so that's one example. Here's another example. So question again would say converge or diverge. If convergent, evaluate. So here's 1 to infinity. So your first step is to rewrite this as a limit. And this is a super easy integral, right? So I just went and did the integral. And then I rewrote 1 to t, right? And 1 to t, because I'm letting t go to infinity. I plug in the top limit, because I should keep absolute value bars there. Subtract off, plugging in the bottom limit. Then I let t go to infinity. ln of infinity, think about what ln of x looks like. ln looks like this, as x's are going to infinity, y's are going to infinity. So this is infinity. And then ln of 1 I know is 0, but infinity minus 0 gives me infinity. So this area does not add up. This is a curious thing. So what does 1 over x look like? 1 over x looks like this. So I'm saying from 1 to infinity, under 1 over x, the graph of y equal 1 over x does not add up. So this adds up to infinity, whereas the area under 1 over x cubed from 1 to infinity, it did add up to 1/2. Very curious. All right, so here we have same question, converge or diverge. If converge, evaluate. So now I've got my negative infinity down here. So first off, start off with writing limit as t goes to negative infinity and put the t down here, right? Down in the bottom limit where the infinity was, or the negative infinity. Keep the 0 up here, and I rewrote this as e to the negative x so that in the next step I could easily take the integral or the antiderivative using the La Jolla theorem. So then carry the limit along. You need to do that every single time. Take the antiderivative, right? E to the negative x over negative 1, and then I'm going to evaluate between 0 and t. So what did I do? I did nothing. I meant to. So what I meant to do was rewrite this as the fraction that it is. Or I guess I didn't. I don't know what I did. No, I guess I wasn't going to. I didn't do that here. So I just rewrote it again. Didn't really do anything. Okay, let's move to the next step. So plug in the top limit. Subtract off, plugging in the bottom limit. Okay, in this step, I'm going to rewrite this so I can see what's happening. E to the 0 I know is 1, so I have negative 1 plus, and then here I have 1 over e to the t. So 1 over e to the t, putting in a negative infinity gives me an e to the negative infinity in the denominator, which comes upstairs to be e to the infinity, or I guess that's why I left it like this. You could just put the negative infinity in here, and the negative times the negative infinity makes e to the infinity. You don't write it, but you think it, and you say, oh yeah, e to the infinity, it's infinity. So it diverges. So these integrals that you'll be doing for these improper integrals will just require u substitution, but you must put the u back in. You must put the x values back in, because remember before we would sometimes change the limits of integration? That's way too hard to do with this limit, with t going to infinity. So always go back to the x's if you have u substitution. And good news is u substitution is the hardest that they get. So you use substitution because we just did a ton of really hard integrals, right? Okay, so here we go. So let's just finish off this one. So here's my integral. So first off, I can see that I need a u substitution. So these are a lot of writing. So yes, you can do a couple of steps in one. So here's my u substitution of u equal negative x squared. So I would get a negative 1/2 du is x dx, right? So x dx would be taken care of with negative 1/2 du. So there it is, negative 1/2 du, and I'd get e to the u. And then I'm rewriting, so I don't have an infinity anymore. I put the t here, and t's going to infinity. Necessary step. So then I take the antiderivative of e to the u, and it's e to the u. And I'm allowed to pull that negative 1/2 all the way on the outside. And so now I'm going to make sure I put the x's back in. Hugely important. So put the x's back in here, and then I'm going to take the time to write this one as a fraction. So this negative exponent puts it in the denominator, and this will help me to see what's happening as I plug in the t, and subtracting off, plugging in the 1. So now as I let t go to infinity, I get 1 over e to the infinity, which is this denominator's infinity. 1 over infinity is 0, and then I've got this left over, so 0 minus 1 over e, and then times this negative 1/2, so I get 1 over 2e. Since this integral goes to a number, I say it converges.